Hello, my name is Andrew Newell, and this is a joint work between myself, Christina Nita Rotaru, my advisor at Purdue University, the two students Daniel Obenshane and Thomas Tantalo, with Yair Amir as their advisor at Johns Hopkins. And this work is on increasing network resiliency by optimally assigning diverse variants to routing nodes. The type of networks we consider are global cloud networks. These are overlay networks which offer highly available communication to clients. They're designed to withstand faults, as you can see in this example. Any pair of clients has multiple paths of routers between them, so even if a few routers happen to fail, the clients may never see disruption in their connection. Typically, these networks are set up in a homogeneous fashion for low management overhead. This poses a problem, however, if there's an attack on the system, as even a single found vulnerability by an attacker can be repeatedly exploited at all overlay routers and compromise every node in the system. Thus, the attacker can definitely disrupt all connections among the clients. The attacks can target any vital component of an overlay router, such as the routing code, the operating system running that code, the physical router connected to that machine, or even the administrator. There are also readily available diverse variants for each of these components due to competing hardware and software vendors, different versions of software, and different personnel to administrate. Each of these diverse variants is still vulnerable, but the key is that they're vulnerable in different ways. So if you deploy multiple variants in your network, even if the attacker succeeds and finds vulnerabilities for some, there still should be a surviving network to offer connections among the clients. Typically, also with these types of diversity, the number of variants is usually limited. So you have only so many vendors to look to, so many versions of software, and so many people. And there are many nodes in the network. So there's a question of how to assign diversity to those nodes. I'll show you the importance of this decision with a simple example. We have two clients connected through 4 overlay routers, and there are 2 paths of overlay routers. And we have these 2 variants, and we want to see how different assignments affect the connectivity of these clients. So in this first case, each path has one of each type of overlay route, each variant. So if the attacker succeeds on red or blue, it succeeded in severing the connection between the clients. In the second example, there is a single variant for each path. So if the attacker succeeds and compromises red or blue, there's still a surviving path to offer connectivity among the clients. The problem is actually easy in the 2-client case, however, it becomes much more difficult when there are more clients. It's easy in the 2-client case, as you can always compute the number of node disjoint paths and put one variant along each path. But when there are multiple clients, you have to satisfy multiple client pairs at the same time, and multiple variants can further complicate things. So the focus of the work, we want to focus on this new problem and how to solve it, and also we want to see what kind of benefits in terms of resiliency you can achieve when you solve this problem well on realistic networks. So for the problem, we're going to first look at the model we assume, the formulation of the specific problem, and algorithms we chose to solve the problem. So we assume that there are a set of clients that need connectivity through a set of routing nodes. And we have a set of variants. Each variant has a resilience, which is the probability that that variant is not compromised. And we assume these probabilities are mutually independent. And this captures the fact that these variants should have different vulnerabilities. We assign one variant per node in the network, and all nodes of the same variant are compromised together. So if a variant is compromised, all nodes assigned that variant are considered compromised. We assume a resilient routing protocol, which means that if a pair of clients is considered connected, if and only if there is a path of routers that are not compromised between them. And with this, we want to maximize a metric of connectivity. Our connectivity metric is expected client connectivity. This is a way to measure the general client-to-client connectivity in a probabilistic way. And it's exactly the average probability that a client pair is connected. So we average this over all im choose 2 client pairs, given that im is the number of clients in the network. And We can compute this by looking at all possible compromise events, which is any set of variants that can be compromised together. And for each one, we take the probability of that compromise event happening, which you can find from the resilience values, and you multiply it by the proportion of connections, which is expressed here as this function f over an assignment A and a compromise event E. So with the assignment, you know which nodes are assigned which variants, and then E denotes which variants are compromised, so you remove those nodes and you find out which client pairs are still connected. I can show you this through an example of this as follows. We have the same topology with two assignments, and at the end of this we'll find out that one of these assignments is superior to the other one based on counting the connectivity and also the final expected client connectivities. So there are 4 possible compromise events as shown in the table as the columns. 2 of them are trivial. When nothing is compromised, all client pairs are connected. In this case, there are 3 client pairs. And if everything's compromised, so red and blue, then nothing should be connected. If only blue is compromised in the left assignment, you have 1 client pair connected. In the right, you have 3 client pairs connected. You have all client pairs still in the right through the red nodes. And if red is compromised, we have 1 client pair connected through the blue nodes on the left, and then 2 client pairs connected through the blue nodes on the right. And you can find these final expected client connectivities by multiplying the values in the rows by the expected client connectivities. So just by the simple counts, you could see that the right assignment had more connectivity than the one on the left, and the expected client connectivity shows that as well. We're multiplying those simple counts by the likelihood that those situations occur. So the specific diversity assignment problem is given a topology and a set of variants with resilience values. How do we want to find that assignment which is maximizing the expected client connectivity. We have a full proof that this is NP-hard in the technical report, and the search space is very large as well. It's the number of variants raised to the power of the number of nodes in the network. However, the good news is we don't have to solve this very often. You just need to solve it at deployment, and you can resolve it again if there are major changes in the topology. So we looked at 2 algorithms, the first of which we tried to solve optimally. We looked at mixed integer programming to do this. Mixed integer program is a linear program with integer constraints. So linear programs are easy to solve. The integer constraints make them hard to solve, but they also make it, you can express NP-hard problems with these types of programs. They're common in operations research for problems such as manufacturing, shipping, or supply chain management, where you want to minimize cost given some constraints that may be combinatorial in nature. So those problems are NP-hard, but despite them being hard, there's still been extensive work in searching for the best solutions or even optimal solutions through creating these mixed integer program solvers. So we leverage this same effort, and our first step is to express our diversity assignment problem as a mixed integer program. So the full details are in the paper. I'm showing you just the first 3 lines of this. There are 7 more. So you have an objective function and then a set of constraints. And notice one constraint here is in red, and that's the integer constraint. That makes this problem hard to solve. However, we were able to solve it on target topologies that we were interested in of 20 nodes. And we were able to do this with Cplex, which is one of these mixed integer program solvers. We didn't try to stress test this technique, but we do know on larger topologies you would fail to find the optimal solution due to prohibitive running time or even memory. It could happen at 50 nodes, probably 100 nodes, you come into lots of trouble, and definitely at something like 1,000 nodes. If you have a very large network, we wanted another algorithm. So we want to see if we could solve at scale, and we used a greedy algorithm to do this. We repeat these 3 steps over and over again until we've assigned the whole network. So the first step, we generate a candidate set of assignments. In the next step, we look through them and we want to pick the one that maximizes the expected client connectivity while minimizing the number of assignments you needed to do it with. And so out of these 3 examples that could happen in the first the first iteration, we would pick the middle one because it has more expected client connectivity than the one to the left, and it also uses fewer nodes than the one to the right. So we'd fix this as the best candidate, and we'd repeat this. So these two nodes colored red in this assignment would stay red, and we'd try other candidate assignments and see what, and pick the best of those and keep iterating. This gives us a nice polynomial guarantee on the running time, so it will complete, but we don't have any guarantee the solution is near optimal. But we did do comparisons on random topologies. So we looked at 3 assignment strategies. We tried the optimal assignment, which is the one from the mixed integer program, the greedy assignment, the one I just went over, and also random assignment. So random is like a baseline. It is a baseline here. And we want to make sure that greedy is performing close to optimal and definitely better than random, so that greedy is actually doing something good. And we want to look at lots of different topologies to make sure that greedy is doing well in various scenarios. So in the left graph here, we fix the density, which is density for us is the average degree each router has. And we vary the number of nodes in the network. And we see that greedy is performing close to optimal and definitely better than random for each of these cases. And then also on the right graph, we fix the number of nodes and we vary the density. And again, greedy is doing well. So we can do pretty well with this greedy assignment. So if there is a large topology where the optimal solution can't be obtained, you can always use this greedy assignment, and we have some belief that it'll be near whatever the optimal solution would be. So we'll do a good job with assignment. So now we move on to applying this problem to a realistic scenario. So we have actually the topology I showed you in the first few slides is an anonymized version of LTN global communications topology, the overlay topology that they use to serve clients. They're a live video streaming service, and they provide highly available connections among clients such that they can stream video between each other. And we want to assume that this topology is under attack. So we assume that we have 3 variants of these resilience values. And I want to point out that we chose these resilience values just to show examples with concrete numbers. In a realistic scenario, if you were to determine these resilience values for different routing configurations you come up with, and they're higher or lower, you'll still see the same benefits of diversity. It's just that all of the final expected client connectivities will either be scaled up or down depending on what the real resilience values are. So we want to demonstrate, we'll look at assignments using just 1, 2, or all 3 of these variants to see the impact of diversity. So this first case is the homogeneous case. The expected client connectivity is 90%. So your network is just as strong as the variant you pick. And the optimal solution is pretty simple. You pick the strongest variant and you put it everywhere. So effectively, your network is either completely alive with 90% chance or 10% chance an attacker found the vulnerability and was able to exploit all of your routing nodes and everything was compromised. So in this case with 2 variants, we get an increase in the expected client connectivity. It's 98.5%. And it's because, one big key takeaway here is that we've added a more vulnerable variant, this blue variant. And by itself, the blue variant is more vulnerable than the red variant. It's worse out of these 2. However, the blue variant fails in a different way than the red variant. So a network can gain a lot by using it. And this happens again if you add the green variant as well. So even though it's worse than the red and blue, you get another gain in expected client connectivity, up to 99.7% compared to you can compare this to the 90% of the homogeneous case. And you can look at this from a different perspective of disconnectivity. So it's just the opposite of connectivity. So you take 1 minus the connectivity to get the disconnectivity. And it's 0.3% for this 3 variant case, versus the 10% for the homogeneous case. So if you're a client parent using this network, then you're 33 times less likely to be disconnected in this case of diversity as in the homogeneous case. So for this high resilience, we didn't just need diversity alone. We also needed a good assignment. This is an optimal assignment, and all the assignments I showed were optimal. If you just decided I'm going to use diversity, you got the 3 routing configurations, and you applied them everywhere, say randomly, you wouldn't do nearly as good. Here's one specifically bad case where you only get 81.1% expected client connectivity. So this is actually even worse than the homogeneous case. You've actually done a worse job for yourself by going to this complexity of adding multiple variants in your network. And we looked at this further. We looked at 100,000 random assignments of the 3 variants to that network. Roughly 20% fall in this category of being worse than the homogeneous case. And even if you take the best of all these random approaches, or all these random assignments, you get 98.8%, which is not optimal. It's actually, in terms of the disconnectivity, it's 4 times worse. So there's a lot to be gained through applying this theory and finding that optimal solution. So far I've been talking about this expected client connectivity metric a lot to maximize, so the goal was to maximize general connectivity of clients, but we wanted to see if we could do better if we know the specific client protocol that was running, which has specific client communication requirements, not just the more the better. So, well, for all protocols, more the better is the case, but if you're able to give up some in certain scenarios, you can maximize more in other scenarios. So we alter our mixed integer program to perform optimization for a specific case. And the specific case we chose was Byzantine fault tolerance, which is a state machine replication protocol that works given that there are Byzantine faults. So replicas are acting in arbitrary ways. They're trying to send messages and mess up the protocol. And the goal of this protocol is to keep a consistent state across multiple replicas, such that each replica can serve a request that changes the state, and then that replica will contact all the others to make sure they all change their state in the same way. So it's used for many important, there are many important applications that use such a protocol. So for our network, we have 10 clients that are using this overlay network, and we want to treat them all as BFT replicas. So for progress with BFT, we need 7 replicas to follow the protocol and be fully connected. Following the protocol is the one that's generally talked about in the literature about BFT, or more generally in consensus protocols, but they do have to be fully connected. Most of the work in this area just assumes that there's a good network that always works, but that's not the case. The attacker could also choose to attack the routers. So we have a different attacker scenario. So one attacker scenario is that you could say that any 3 replicas could be compromised because you only need 7 replicas to follow the protocol for it to work. But we choose to have only 1 replica that can be attacked. But at the same time, so the attacker's a little weaker in that sense, but the attacker is also stronger in the sense that it can attack the network and try to partition the clients. So from the network's perspective, for BFT to make progress, the network needs to put 8 clients in a connected clique, since the attacker can pick one of those 8 clients to be malicious, and then you're still guaranteed to have 7 clients that are fully connected in a clique and are following the protocol. So the difference now that we're not optimizing for general connectivity, but we're optimizing connectivity for this protocol, is that we really only care about the 8 cliques. Any connections beyond that don't help us, so we stop striving for those extra connections here. So in this little figure, we cared about connecting all 8 together, but those extra few connections to those last 2 nodes, they won't be counted as anything good. And also, if you can't connect an 8 clique, then it won't try to connect any clients at all in certain compromise events, because it just doesn't help for that client protocol. So we want to see how these assignments differ between maximizing for the general connectivity and maximizing specifically for this 8-clique probability. And we also want to see how that affects resilience. So for the first case, optimizing for general connectivity, we added an extra variant for this case, and one more connection from each client to the network to make this a more interesting case. So the expected client connectivity goes a little bit, increases a little bit. It's at 99.75% compared to the 99.7% from that we found previously because of this extra variant and extra connections. And notice that it only chose to use one yellow variant. So it's running out of no disjoint paths between the clients to use a lot of yellow variants and try to get a lot out of this new variant. So it just chooses to put it one place. So it really wants to make lots of 10 cliques and lots of different compromise events of where red, blue, or green are not compromised. And given this, you have an 8-clique probability of just 99.7%. So this is the probability that BFT makes progress. So you can do better if you optimize for that 8-clique probability. So now we built into the mixed integer program the ability to optimize specifically for trying to maximize the probability that an 8-clique forms among the clients. So this one difference you see in the assignment is that you're using more of the yellow nodes. You're actually using each type of node more equally. And with this, the optimization is able to find more compromise events where it can connect 8 clients in a clique than it could before. Because in certain compromise events, it only connects 8 together, and then it forgets the last 2 because it really doesn't need them for progress in those cases. So given this assignment, if you're running BFT at the clients and the network's being attacked, you will have a greater chance that BFT is running and serving requests and making its progress that it needs to make. The drawback is that you do sacrifice general connectivity. It's gone down to 98.06%. So if there's another protocol running among the clients, you could suffer from that. So this would be a design decision that would have to be made by the network. So in conclusion, we propose a new problem that's vital to constructing these resilient networks through diversity. Our motivation for this work came from global cloud networks. However, when we noticed that this issue, we really thought of this problem in a very general way. These networks could be any type of network. They could be wireless mesh networks, ISPs, the same theory will apply. And also, the type of failures don't necessarily have to be intrusions. They could be correlated benign faults. So if you have some type of software that you know if a bug occurs, it's going to occur in all of the overlay routers at the same time, then you could have multiple types of software and hopefully only one type will fail. And the same theory applies there as well. And then lastly, I want to point out there's a lot of work from the computer security community and how to create these resilient, or how to create resilient systems through through compiler techniques, through software security techniques, etc., and how to harden this code. However, I mentioned in the first few slides that we could deal with attacks on the administrator. So that's one place where this work is really unique. So even though the other techniques for computer security can be used in conjunction with this diversity, really we provide a unique solution when you have these administrators that are sometimes weak to phishing attacks. They could even be bribed, or they might have weak passwords. Because you can give each administrator its own private key such that it only has access to some set of the network. Thanks for listening to my talk, and if you have any questions, feel free to email me at this address.